It is very difficult to understand a lot of this stuff with electricity unless we understand what the units are and what they mean. So some of these are going to look foreign to you. Coulombs looked foreign to me. So I had to do what? CK12, the lesson is you throwing around this term Coulomb, and I'm not familiar with it. I need to search it up, right? So you guys, when we're getting into this stuff that's foreign to you, think, okay, what do I understand? What don't I? I need to fill in those gaps. So I had to fill in a gap this morning, okay? Now, I'm not going to say I understand it perfectly yet. We'll use it, and then I'll get better with it, but at least I have a basic understanding now. But I want to get you all there too with electrical units. Let's start off with some that you probably are already familiar with. How many of you have ever heard of watts? Okay, good. So watts measure what? Electrical power. Yes. Electric power. How powerful your microwave is, for example, depends on, it can be measured in wattage. A standard household microwave is somewhere around 1,000 watts, depending on the model. Okay? The formula to find watts, or the wattage of something, appliance perhaps, is watts, capital W, is equal to amps times volts. Okay, but Mr. H, what the heck is an amp or a volt? Are you familiar with those terms? Yeah, a little bit. You've heard them before, right? So amperes, let's do that one. Amperes, or just amps for short, they measure flow or current. And then we have V for voltage, or just volts. Voltage is like the pressure. It's the potential energy. Now, I've heard a bunch of people use this analogy, and after using it myself a few times teaching this, I think it's a good analogy. How many of you all have ever used a garden hose? Okay, so the analogy is between electricity in a circuit and water flowing through a garden hose. Okay, we're going to compare the two. Wattage is like you want to clean off a sidewalk with the garden hose, with the water out of the garden hose, okay? How much power can be applied to the sidewalk as far as cleaning power would be like the wattage, okay? I don't know if that's making sense yet. Current, amps, how much electricity is flowing through a circuit would be analogous to how much water is actually coming out the hose. The flow, current or flow, okay? And then voltage is like putting your thumb over the end of the garden hose. It increases the pressure, right? So if you think about it, okay, how much water is coming out of the garden hose plus how much pressure we apply determines how much cleaning power, right, that you can actually clean that sidewalk off with your garden hose. So same thing, how much electrical power you have depends on the total amount of electrons flowing through the circuit, the current, the flow, times the pressure, the electrical potential energy, the voltage. So watts, power, is equal to amps, the flow, times voltage, the pressure. Okay? Does that kind of sort of make sense? So I'll give you an example. The microwave, okay? We said that a standard microwave, we'll say, is 1,000 watts. And in the average household, okay, I say average, basically all households in America, if you're using this standard standard two-prong with a ground, right, outlet type, that's 110 volts, 110 to 120 volts. So let's say 120 volts. To find the amps, what would we do? You what? Divide. Divide what by what? Yep. So we do both sides. To get the amps by themselves, we divide out the 120 volts. Do it to that side, you have to do it to this side. So then we just say, what's 1,000 divided by 120? I mean, if you need to use a calculator, go ahead. Say again. 8.3. Repeating. Ooh, not power. Amps. So the current. Okay. Now I want you to think about something. How many of you all have ever looked in your electrical panel at the house? Ever seen it? That metal door, you open it up and there's all those little switches, right? Those are circuit breakers. They're called circuit breakers because they break the circuit. They stop the flow of electricity if there's a problem. Okay? Each one of those circuit breakers, if you look at them, there's a number on them. Most household circuits nowadays are 15 amp. In the kitchen or in the garage, you'll see maybe 20 amps because there's heavier duty equipment that uses more electricity. 8.3 amps, is that more than half of 15? What's 8.3 times 2? 16.6, right? So it's more than half of 15, isn't it? So if you've got a circuit with just one appliance, just a microwave, and by the way, the ones that are up over the stove, how many of you all have a microwave that's up over the stove? Okay, those are pretty common. Those are usually on the higher end of that 1,000. So like if you have a countertop microwave, it might only be 800 watts. And like the small one I have in there. And then on the bigger end, you might have a 12 or 1,300 watt microwave up over the stove. So in the middle, we're just using 1,000 as an easy number. That's already 8.5 amps, which is more than half of what a standard household circuit would handle. I'd be willing to bet that at least a few of you, if you went in your circuit breaker, you'd have a dedicated breaker just for your microwave. In other words, only the microwave is on that line because it takes so much power. Does that make sense? The electricians, when they design these houses, as far as where the plugs will go and which plugs will be on which circuits, a microwave nowadays, I don't know if it's code, but it's very common that they'd have their own circuit. Does that make sense? You can't put much more than that on a circuit. For example, if you had that on there and plus you had another kitchen outlet, let's say, and you had a toaster plugged in and you tried to have the toaster going and the microwave going at the same time, what would happen? It would overload the circuit because the circuit has certain gauge wire. A 15 amp circuit would only have 14 gauge wire. It can't handle that much flow. It would melt the copper wire. It would overheat, could start a fire. So the circuit breaker detects that there's too much flow trying to go through the line and it breaks. The circuit breaker breaks the circuit. It's temporary, it's just a switch, right? So you can turn it off, turn it back on again. So that's why microwaves often have their own dedicated circuit. All right, cool. Next one. Do you guys have any questions on watts, amps, or volts? Fantastic. Let's get this stuff out of the way. I'm going to leave those up. Here's another one. Ohms. Okay? Ohms measure resistance. So we were looking at, categorizing things as either conductors or insulators of electricity. Ohms measures, well, how conductive or how resistant to that flow is that material, okay? So in any circuit, for example, you can measure the resistance with an ohm meter. I think that's what it's called. So the symbol for this is kind of goofy. Looks like that for an ohm. And the formula, make sure I got this right. Volts equals amps times ohms, or resistance. So the flow times, or the current, right, times the resistance gives you the voltage. Now think back to our garden hose analogy. So you have the pressure, right, is determined how much voltage, well, how much flow times how hard you're pressing with your thumb. Does that make sense? So the resistance is your thumb. The amp is how much water is going past your thumb. How hard you push on that water gives you the voltage. Does that make sense? But we're talking about electricity, not water. So the resistance is provided by whatever material you're trying to use as a conductor. How easily do the electrons flow through it? And then amps, again, the flow, how many electrons are trying to get through that material. So those two multiplied by each other gives you volts. So let's say we know our voltage. We'll stick with the standard household, 120 volts. And let's say we have, let's use that microwave, for example. We said it was 8.3 amps. And we want to know the resistance in the line. How much resistance is in our circuit? So you can do the math real quick and figure that out. So what do we need to do? We need to isolate the variable. So we divide it out, 8.3 on both sides. What's 120 divided by 8.3? Repeating. $14.4 ohms is the resistance in that circuit. Okay? Relatively simple. All right. Give you a second to copy that down, and we'll move on to the next one.
Yeah, good pass.
All right, I'm not going to get crazy into this one. I'm not even going to do an example because we're not there yet. I'm just acquainting you with the units, okay? This one is a coulomb. And it's abbreviated with just a capital C. A coulombs equal amps times seconds. Finally, one we knew, right? We all know seconds. tomorrow's lesson got some math, so I want to lay some decent groundwork, not just for you all, for me, right? I'm learning some of this stuff for the first time too. Probably not supposed to say that to your students, but like, if I ever learned Coulomb's law, I don't remember it, like, at all. So I'm learning this stuff too, or relearning it. Filling a gap in my knowledge.